Damn it, we're going to crash!
Just 4 minutes and 10 seconds. That's all it took for a state-of-the-art Airbus A330 to fall out of the sky. From cruising at 38,000 feet down into the depths of the Atlantic Ocean. 4 minutes, not enough time to finish a cup of coffee, but enough to lose an entire aircraft, its crew, and 228 lives. How could a modern airliner spiral into chaos so quickly, without a single distress call? What happened in the cockpit?
I don't know. I don't know what's happening.
What did the pilots see? And what did they miss? Let's break it down, second by second. On the evening of May 31st, 2009, an Air France Airbus A330 took off from Rio de Janeiro. It was scheduled for a 13-hour overnight flight to France, crossing the entire Atlantic Ocean. The aircraft was only 4 years old, but it had a minor issue with the heating system of the pitot probes. These probes measure dynamic air pressure, used by the aircraft's computers to determine indicated airspeed. This speed is crucial for flight, as lift is generated by the air flowing over the wings, keeping the plane in the sky. Over the previous year, the crews had filed 9 reports about unreliable airspeed readings during flight. The heating system wasn't always effective, and the pitot probes would get clogged with snow and ice. Similar incidents had occurred on other Airbus aircraft as well. It was a systemic problem, already known to the manufacturer. A technical bulletin was issued to upgrade the probes, recommending they be replaced across all Airbus models at the manufacturer's expense. However, the bulletin was only advisory, because airspeed loss was usually brief and not considered dangerous. All pilots had also trained for such scenarios in simulators. Upon landing in Paris, this A330 was scheduled for maintenance, including replacement of the pitot probes. The Rio de Janeiro to Paris flight was long, so a relief pilot was included in the crew. He was there to substitute for the others so that everyone could rest. In the cockpit were experienced pilots, the 58-year-old captain and the 32-year-old first officer, who was, in fact, the least experienced among them, with around 3,000 total flight hours and 800 on type. The 37-year-old relief pilot was seated on the jump seat in the cockpit. At 7:30 p.m. local time, they departed Rio and headed north along the Brazilian coastline. Takeoff and initial control were handled by the first officer. After climbing through 20,000 feet, the relief pilot went to the crew rest area, located behind the cockpit. Sometime later, the aircraft reached its initial cruising altitude of 35,000 feet. As fuel was burned, the crew planned to climb further to 37,000 feet to improve fuel efficiency. 3 hours into the flight, the aircraft entered a cloud layer and light turbulence began. These clouds weren't dangerous, but their development needed to be monitored. The radar now showed hazardous areas with significant turbulence. These had to be avoided. The captain didn't see a major threat, but pointed out the appearance of bright flashes ahead, known as St. Elmo's fire. This phenomenon is caused by a corona discharge in an area of high atmospheric electric field. He pressed a button on the overhead panel, triggering a chime in the crew rest area. The relief pilot returned to the cockpit and swapped places with the captain. It was 11 p.m. Rio time. The first officer continued flying the aircraft. The captain went to rest, leaving the other 2 pilots to face the uncertain weather conditions. Both were already tired and wanted to sleep. 8 minutes later, a chain of events would begin, one that would lead to disaster. The relief pilot moved his seat back into a relaxed position. To avoid a storm cell, he asked the first officer to adjust the course.
Would you mind turning a bit to the left?
Sorry?
Maybe we should go slightly left.
The first officer rotated the autopilot heading knob 12 degrees to the left. And then, the pitot tubes failed. The aircraft's computers lost information about dynamic pressure, which meant they no longer had reliable airspeed data. Autopilot and autothrust disconnected, as designed. A strong gust of wind rolled the aircraft to the right. The first officer grabbed the side stick. Both pilots were under extreme stress and became disoriented. Due to the loss of total air pressure input, the computer recalculated altitude and falsely showed a sudden drop of 100 meters. The first officer instinctively pulled the side stick left to level the wings and back to climb. But the aircraft hadn't actually lost altitude. This input caused an increase in pitch and initiated a steep climb. The stall warning sounded. With the airspeed data gone, the aircraft switched into alternate law, a degraded control mode.
The Airbus is a fly-by-wire aircraft. The pilot doesn't directly control the ailerons or elevators. By moving the side stick, he sends commands to the flight computers, which then move the control surfaces. Under normal conditions, these computers act as a protective layer, preventing the pilot from making dangerous inputs. For example, they won't allow the nose to pitch up too steeply or the aircraft to bank too far. But now, with no data from the sensors, the computers are essentially blind. All protections are disabled.
The flight controls became unusually sensitive. So when the first officer sharply moved the side stick to the left, the aircraft rolled abruptly from a right bank into a left bank. This sudden reversal was not necessary and marked the beginning of a dangerous oscillation. The first officer began swinging the aircraft from side to side with overly aggressive inputs. His full attention was on the bank angle, trying to level the wings using the artificial horizon. But he was no longer monitoring the pitch, which continued to increase because he was still pulling the side stick back. In normal flight, protection systems would stop this. Now, without those protections, the nose kept rising. The aircraft climbed steeply while losing airspeed, like a sled pushed uphill. It traded speed for altitude. The first officer re-engaged auto thrust, which increased engine thrust. This created an additional nose-up moment, causing the pitch to rise even further. The cockpit filled with alarms, intensifying the already high stress. The aircraft was now climbing at a vertical speed of 35 meters per second, twice the normal rate during takeoff. The flight director bars disappeared and then reappeared, showing pitch guidance that matched the excessive climb rate. This only confused the already overloaded first officer. The relief pilot tried to intervene.
Watch your speed.
Okay, I'm going back down.
The first officer pushed the side stick forward, but only slightly. It wasn't enough to bring the nose down.
Push down. All three displays show we're climbing, so push down again.
Okay.
Instead of following the procedure for unreliable airspeed, setting a 5-degree pitch and fixed engine power, the first officer reduced pitch only to 10 degrees. The aircraft continued to climb rapidly. He began to lose situational awareness. The relief pilot pressed the call button to summon the captain, but the captain didn't respond. The stall warning sounded again, but neither pilot reacted properly. Instead of lowering the nose, the first officer instinctively pulled back on the side stick, increasing the pitch even more.
A stall can occur due to a loss of speed, or if the nose is raised too high. In this case, the airflow over the wings is disrupted, and the wings stop generating lift. The aircraft enters a stall, accompanied by vibrations and a loss of control effectiveness. Most modern commercial aircraft can recover from a stall in its early stages if the pilots act quickly. They must lower the nose and set maximum thrust.
The altitude was already very high. At such altitude, flight is difficult because the air is extremely thin. Its density is not enough to keep the aircraft aloft. Due to the lack of speed, the aircraft stopped climbing and entered level flight. However, it continued flying with its nose pitched up, rocking side to side. The first officer tried to counter these oscillations, but he only made things worse. On aircraft with a yoke, an approaching stall is accompanied not only by aural warnings, but also by strong yoke vibrations. On the Airbus, there is no yoke, and the side stick does not vibrate. The pilots are warned only by sound. However, under extreme stress, human hearing becomes less sensitive. That's why the pilots ignored the continuous stall warning.
The aircraft reached a critical angle of attack. Now, severe buffeting shook the entire airframe. The first officer set the engines to toga, maximum power. But at this altitude, the engines were almost ineffective. The aircraft was close to its ceiling, 41,000 feet, and there was too little air for the engines to produce sufficient thrust. The relief pilot tried to tell the first officer to be more gentle with the side stick, but it didn't help. The first officer kept making aggressive side-to-side inputs. The Airbus gained a bit more altitude, reaching 38,000 feet, or 11.5 kilometers, and then began to descend into the Atlantic Ocean. The airspeed indications came back, but the crew had already lost control of the situation. For the next 40 seconds, the first officer continued to pull the side stick toward himself. This was an instinctive reaction, but the aircraft was in a fully developed stall, and pulling back only made things worse. The relief pilot pressed the priority button on his side stick and took control, but he also failed to recover the aircraft. To get out of the stall, he needed to push the side stick forward and set the engines to toga. The aircraft was now descending with a vertical speed of 50 meters per second,
like skydivers in free fall. Because of the loud noise of the wind outside, the first officer mistakenly believed that the aircraft was flying too fast forward. At 36,000 feet, the captain returned to the cockpit. He could not understand what was happening. Only 3 minutes of flight remained.
What are you doing?
I don't know. I don't know what's happening.
We're losing control of the aircraft.
We've lost all control of the aircraft. We don't understand anything. We've tried everything.
Until the end of the flight, the nose remained pitched up. Neither the first officer nor the relief pilot ever realized that the aircraft was in a stall. They kept trying to recover, but continued to lose spatial orientation and control over the aircraft.
What do you think? What should we do?
I don't know. It's going down. I'm descending.
You are descending.
No, you're climbing! The aircraft passed through 20,000 feet. The confusion and panic in the pilots' conversation only grew. They pressed the rudder pedals, took control from one another, deflected the side sticks in different directions, and set the engines to toga. But nothing helped. The aircraft plunged past 10,000 feet. Now both pilots were randomly pulling on the side sticks. The aircraft's flight control system averaged their inputs, which made control even less effective. In the final seconds, the captain began to understand what was going on.
No, don't climb! Descend! Look, you're pulling the nose up.
At 4,000 feet, the cockpit voice alert sounded. Sync rate, pull up. The relief pilot again pulled the side stick fully toward himself.
I'm pulling back! I'm pulling back!
Don't!
But we have to. We're at 4,000.
Come on, pull back.
Come on, pull!
Damn it, we're going to crash!
With enormous vertical speed, the aircraft slammed flat into the Atlantic Ocean. It shattered upon impact with the water. All 228 people on board died instantly. About an hour later, air traffic control centers began contacting each other. Flight 447 had not checked in with any of them at the scheduled time. Controllers contacted other aircraft flying in the same area, asking if anyone had received any messages or emergency signals. No one had heard anything from the missing A330. 3 hours later, the flight was officially declared missing. Search and rescue aircraft, helicopters, and naval vessels were dispatched to the estimated crash site. 2 days after the accident, the first pieces of wreckage were found floating on the ocean's surface. That marked the beginning of a search operation that would last for 2 years. In 2011, at a depth of 3.5 kilometers, investigators finally located the wreckage of the aircraft and its flight data recorders. The black boxes were found to be in good condition, The analysis revealed that the pitot probes and their heating elements had been temporarily overwhelmed by snow and ice. This caused the loss of reliable indicated airspeed, which in turn led to a chain reaction. The automatic systems of the aircraft disconnected. According to procedure, when speed readings are unreliable, the pilots must set the pitch to 5 degrees, apply a specific engine thrust setting, and maintain level flight. Instead, they raised the nose of the aircraft, causing the airspeed to drop. Eventually, the pilots brought the aircraft into a stall, which they failed to recognize. To recover, all they needed to do was lower the nose and set the engines to maximum power.
After this crash, the design of the pitot probes and their heating systems was modified on all Airbus aircraft. Flight procedures were improved. New simulator exercises were introduced for pilots. This tragedy became a turning point for aviation safety, reminding us that even the most advanced systems depend on human understanding and reaction.